Jai Hind. Today we are going to discuss the topic of predicate logic. In this particular topic, we'll talk about propositional logic. We'll start with the concept of propositional logic. Then we'll talk about theory of predicates and formulas. Then what are predicates, what are quantifiers, the main base of predicate logic. And then we will talk about the inference theory in predicate logic. So, all my topics, all my examples are from the text of Discrete Mathematics and its application from Rosen. So, let us start with the topic. So, we are going to discuss predicate logic. What predicate logic is? It talks about quantifiers and predicates, and what else is present, that is the base, that is propositional logic. So, actually predicate logic in addition to propositional logic, in which we are adding predicates and quantifiers. So, let us start with an introduction to propositional calculus. So, what is propositional calculus? We will talk about the propositions, what it consists of, and the connectives. So, what a proposition is? A proposition is a declarative sentence that declares a fact. It is either true or false. So, the statements which are either true or false but cannot take both the values, those are called propositions. So, we can understand the concept with this particular statement. What the statement is: New Delhi is the capital of India. So, what it is? It is true, it is a fact. Ghaziabad is capital of India. This is false. It is not true. So, it is assuming the value true and it is assuming the value false. If I talk about 1 plus 1 is equal to 2, we know that 1 plus 1 is 2. So, this is true. 2 plus 2 is not 3. So, it is false. So, these are some examples of propositions. So, what propositional calculus is? It is containing propositions which are the sentences, declarative sentences, which can take only value true or false, but not both. There are some connectives that we use in our propositional calculus. Let me say I am having a proposition that it is cold today. So, it is a proposition, and another proposition, it is sunny also. So, I am having two propositions, it is cold and it is sunny. So, these are two propositions. These propositions can be used to form compound composition, compound propositions. Those are the compound statements. So, if I talk about it is hot, it is a single statement, it is a primitive statement, it cannot be broken in two parts. But when we are having two and we are connecting that with connective, that forms a compound proposition, compound statement. Okay. So, now let us start with a discussion of a few connectives in our propositional logic that we also use in predicate logic. So, one is negation. In negation, what we are having, if the proposition is true, its negation will be false. If the proposition is false, its negation will be true. So, this is the negation operation. Negation of true is false and negation of false is true. There is another connective or. We call it disjunction. What does it mean? It means two propositions are there, P and Q. What is disjunction of these two? The disjunction will be true if any of these propositions are true or both are true. It means it is false in only in one case, when both the propositions are false. Another connective is conjunction, the AND operator, P and Q. So, what is conjunction? The conjunction of two propositions P and Q is true only when both the propositions are true, otherwise it is false. If both the propositions are true, then the answer will be true, conjunction will be true. Another connective is exclusive OR. What is exclusive OR? Exclusive OR is true when both the propositions are different. It means if one is true and another is false, then the exclusive or connective is true. If both are same, that is either true or false, then the proposition, the exclusive or connective will be false. Now, these are basic connectives. What else we have in propositional logic? That is conditional statement. So, we can have one side conditional statement, or it could be biconditional. So, we call it implication or by implication. So, let us understand the concept of implication first. If we are given two propositions P and Q, then if we are having some conditional statement like if P then Q, it means if P is true, then Q should be true. So, this is implication. This we call conditional statement. This condition, if P then Q, is represented with implication. So, what the statement is, if P is true, then Q should be true. So, when P is true, the implication will be true. So, this is condition on Q, that if P is true, then Q should be true. If P is not true, then there is no condition on Q. If P is not true, then there is no condition on Q. Okay. So, when P is false, the implication will be true. But what is the condition? What is the statement? If P, then Q. What does it mean? It means if P is true, Q cannot be false. So, it is false only in one case, when P is true, but Q is not true. Because what the statement says, if P is true, then Q should be true. This is our implication. Next is by implication. This is by conditional statement. It says that P implies Q and Q implies P. It is conjunction of both the implications, P implies Q and Q implies P. What does it mean? It means if P is true, then Q should be true. If Q is true, then P should be true. So, if we are having two statements, that is P and Q, and P is true and Q is true, then implication will be true. If P is true, Q cannot be false. So, implication will be false. If Q is true, P cannot be false. So, implication will be false. If both are false, there is no condition on either of the two. So, the implication will become true. So, these are our connectives that we use in propositional logic or propositional calculus. Now, an important point here, all these operators, all these connectives have an order of precedence. If we are having some logical formula, some propositional formula, then firstly a negation will be applied. It is having the highest precedence. The second precedence is of and, then of or, then implication, then by implication. So, this is the order of precedence. So, these are our connectives in our propositional logic. Now, when we are having a conditional statement, P implies Q. Our conditional statement given is P implies Q. Then for each conditional statement, there are three important concepts. What are those? Converse, contrapositive and inverse. If P implies Q is the statement, then its converse will be Q implies P. So, what converse is? That is Q implies P. This is converse of the statement, conditional statement P implies Q. And the proposition not of P implies not of Q is called inverse. Not of P implies not of Q is called inverse. The contrapositive is not of Q implies not of P. So, we are having converse which is P, we are having converse which is Q implies P, contrapositive, which is not of Q implies not of P, and then we are having inverse, which is not of P implies not of Q. So the conditional statement has 3 other forms also, the related forms also. Tautology and contradiction. A compound proposition that is always true, no matter what the truth values of the propositional variables that occur in it. It is called tautology. So what is a tautology? In which always we get the true answer. The compound proposition will always be true. And if the compound proposition is always false, that is called contradiction. If it is always true, then tautology. If it is always false, then contradiction. A compound proposition that is neither a tautology nor a contradiction is called contingency. So we are having a specific type of compound proposition. For all true, we call it is a tautology because it is not depending on the values of the propositional variable. It is always giving us true value. That is a tautology. And few statements are there which always give false value. So those are contradiction. Others which are not which are not tautologies or contradiction, it means they are having at least one true, at least one positive. Those are called contingency. Logical equivalence. The compound propositions P and Q are called logically equivalent if P by implication Q is a tautology. What does it mean? It means if P then Q and if Q then P. So in that case these are called logically equivalent. If this is a tautology, it is the two compound statements are logically equivalent. So when we will have the logical equivalent propositions, so we will get the same truth table for those two. And this is the notation we use, logically equivalence. When we write this, it means these two are logically equivalent. For example, P implies Q is logically equivalent to not of P or Q. So what is use of logical equivalence? If I have to remove somewhere implication, so I can use its equivalent formula, logically equivalent formula. So implication P implies Q, I can change with not of P or Q. So that is use of logical equivalent formulas. Now predicate logic, the topic that we are going to cover today, that is predicate logic. Now what the predicate logic is, the area of logic starts with propositional logic, but the area of logic that deals with predicates and quantifiers is called predicate logic or predicate calculus. So the complete propositional logic is available here, that is also included in this. But what else is included? That is the predicates and quantifiers. For example, if I say that all men are good, so what is my thing? I have to tell in some way, I have to represent this knowledge in some way that all. So for all, what I want? Quantifier. Okay, now what else I know, what else I want to present? That these X are good. So what is the way to present it? That is a predicate. X is good or not. So good is my predicate here. For example, if I say for all X, Px. So this predicate is true for all the values of X. So now what we will discuss? We will discuss these two parts. What are these? These quantifiers for all X and existential and the predicates. So let us take both the topics. So first one is predicate. Let us understand the concept of predicate with an example. Let me say I have a statement X is greater than 3. So X is greater than 3 has two parts. One is X and other is the condition, the predicate is greater than 3. So we are having two parts in this. I was having the statement x is greater than 3. So what I am talking about? I am talking about the condition on x. So x is my subject and the condition is the predicate. What is the condition? Is greater than 3. So it is that actually the property that the subject of the statement can have. So what I said, can have. So if I write 4 is greater than 3, so x can have value 4. So I wrote 4 greater than 3. So now what the point is? It is true, condition is true. Now it has become a statement. We can denote the statement x is greater than 3 by px, where p denotes the predicate is greater than and x is the variable. So what we call it, this statement is said to be the value of the propositional function p at x. So what was my x? What was my predicate? I wrote it with the function px. What was it? X greater than 3. This is my function. Now if I put value here, p4, now what will be there? 4 is greater than 3. So now it has become a proposition. This was the propositional function. Now I put a value for x. Now it has become a proposition and its value is true. Now if I enter 2, now what is my condition? 2 is greater than 3? No. So it is false. So it is another proposition. So one proposition was true and another proposition has false value. Okay, so my conditions have been represented with help of a function, propositional function. So whatever is given to us, that can be represented like this. For example, we took on last page that x is good. So I took good as the function name. So what is that? X is good, and in bracket I was having x value, that was the subject for which we are checking that is good or not. Now what are n-ary predicates? If we consider that example of px, in that I was having just one variable. Now what is n-ary predicate? If I am having n variables, a statement involving the n variables x1, x2, xn, so it is n-ary predicate. It can be represented as p x1 comma x2 up to xn. Now I am having two variables. For example, if I write p xy, it's binary predicate. In this I am having two variables. A statement of the form p x1, x2, xn is the value of the propositional function p at the n tuple. So I will put the values of x1, x2, xn. According to that, it will become the proposition. Whatever is the condition given, whatever is the predicate given, that will be checked on based on the values of x1, x2, xn. So we can have any number of variables in the predicate. So we have talked about predicates. We discussed on the slide that predicate logic is actually the propositional logic plus which deals with predicates and quantifiers in propositional logic. Along with propositional logic, so it becomes predicate logic. So now second one is quantifiers. We are having two quantifiers, so let us discuss both the quantifiers one by one. The first one is universal. The universal quantification of px is the statement px for all values of x in the domain. So whatever is the domain given, it will take any value from the whole domain and it will be for that. It will be true for all the values of x in the domain. The notation is for all x px. So what we can write? For all x px. It means universal quantifier. Whatever will be the predicate, it will be true for all the values of x. So we read this as for all x px or for every x px. An element for which px is called counter example of this. So, we can if the condition is not true and for which it falls, that is the counter example. But what is actually universal quantification? It will be true for all the values. So, if we give counter example, it means it is not true for all. Second is existential quantifier. So, what is existential quantification? The existential quantification of Px is the proposition there exists an element x in the domain such that Px. What was in universal? For all x in the domain. Now, we are having there exists 1. When we say there exists 1, it means Px is true for at least 1. What is the notation used? There exists x Px. There exists Px is the notation for existential quantification. Here it is called existential quantifier. So, let us take an example. Px is x square is greater than 0. X square is greater than 0. Now, we will see for all x Px is true or not, there exists x Px is true or not. Okay. So, when I take for all x Px, it means I take any value of x 0, 1, 2, 3, minus 1, minus 2, minus 3 from integer domain, whether it is true or not. Okay. So, if I take 1, it is greater than 0, minus 1 square is greater than 0, 2 minus 2 square is greater than 0, but there is a counter example. For 0, x square is 0. So, in that case, it is not true. So, this assumes false value. Which one? Px. What is Px? X square is greater than 0. So, it assumes false value for all x Px. Now, there exists x Px. So, for there exists, there should be at least one value. So, if I take 2, we know x square is 4, which is greater than 0. So, this will be true. So, what domain I have taken? I have taken the domain of integers. For integer domain, this particular predicate that x square is greater than 0, it will be false for all x Px, but it will be true for there exists Px. The quantifiers for all x and there exists have higher precedence than all other logical operators from propositional calculus. It is having the highest precedence. So, firstly it will be checked, it will be solved and then some other. That is why in clause form, firstly we remove these implications. Now, we are given quantifiers. So, now we will discuss how to do what we mean by negation, negating quantified expressions. So, what is negation of for all x Px? For all x Px means Px, the predicate is true for all the values of x. Now, I am saying that negation of this. So, when negation will be true, when we will get one counter example. It means there exists x for which Px is false. It means there exists x such that negation of Px is true. Negation of Px is true means for this particular x, Px is false. So, in negation, the for all is converted to there exists x. It means for this we get a value for which it is not true. Same way, what is negation of there exists x Qx? There exists Qx says that Qx is true for at least one value. It means there exists one value for which Qx is true. Now, if we are taking negation of this, it means there is no value. When we are saying for all x, there exists x Qx, it means negation means there is no value. Okay. When there is no value, what does it mean? It means for all x, its negation is true. For all x, its negation is true. We can write it like we have taken an example. So, if I have to take negation of for all x, x square is greater than x. So, it will become there exists x. The negation will become there exists x not of x square is greater than x. What does it mean? It means there exists x such that x square is less than equal to x. There is x, what we said, not of x square is greater than x. It means x, for some value x square is less than equal to x. Same way, there exists x such that x square is equal to 2. Okay, so when we take negation of this, it means for all x not of x square is equal to 2. So what it becomes? It becomes there exists x square is not equal to 2. So in negation, the for all converts to there exists, and there exists converts to for all x, and we take the negation of the predicates. So now we will understand the predicate logic with examples. So now we have studied the predicates, and after that we studied about the quantifiers, and before that we are aware that it also includes propositional logic, the propositional calculus. It means we are having the connectives of negation, conjunction, disjunction, implication, by implication. So our example is, I have taken the example from the textbook only, which I mentioned on the slide of contents, that is discrete mathematics and its application. So what are my example? My examples are all lions are fierce, some lions do not drink coffee, some fierce creatures do not drink coffee. So how to present this using predicate logic? So what is our first statement? All lions are fierce. So when we are saying all lions are fierce, it means we are talking about the predicates are true for all. So if I say Px says that x is lion and Qx says that x is fierce. So what is my condition? My condition is if x is lion, then x is fierce, and it is for all. So which quantifier will be used? For all x, if x is lion, then x is fierce. So Px implies Qx. Now what is the second point? Second point is, second statement is some lions do not drink coffee. Now we are not talking about for all, we are talking about some. Some means there exists. Okay, so when we are talking about there exists, so again I am having the predicate that lion, or the second predicate is about coffee. So what we are having, there exists one value of x for which x is lion and x do not drink coffee. So what we have referred here? Some lions do not drink coffee. It means when I am saying some, it means there is one. It may be many, but what we are talking about, some. So it means at least one is there. So there is one x, there exists x such that it is lion and do not drink coffee. Now third statement. So see what we are doing, we are representing our knowledge in terms of predicate logic. So we are taking predicates depending on our requirement. For example, my requirement was to check x is lion. I am not saying x is goat. We are not talking about goat is fierce or not. So what is my condition? My condition is on the domain of animals ki if x is lion, then x is fierce. Okay. So now what I am saying in third one, again some. Some means there is at least one. Maybe many, but at least one is there, because we are saying some fierce creature. Fierce means we have taken for fierce Q. The predicate was Q when we were talking about all lions are fierce. Now, if some fierce creatures, it means there is some value which is fierce, do not drink coffee and do not drink coffee. So there exists x such that x is fierce and x do not drink coffee. So this way we have used the predicate logic to represent our knowledge. we can take another example also. If we consider this example, in this example what we are talking about, we are talking about 4 statements. All hummingbirds are richly colored. No large birds live on honey. Birds that do not live on honey are dull in color. Hummingbirds are small. These are our statements. Okay, now what we are talking about? We are talking about birds now. And what condition we are talking about? Bird is hummingbird. And what else we are talking about in first statement? That is of color. And color we are saying rich in color, and in other statement we are saying dull in color. So we can take one predicate as rich in color. So all hummingbirds, for all x, if x is hummingbird then it is richly colored. For richly colored we have taken the predicate sx. Okay. Second one is no large birds live on honey. It means there is not existing, there doesn't exist any bird which is large. For large we have taken here qx and live on honey. Bird live on honey, for this we have taken the predicate rx. So no large bird, there doesn't exist any bird which is large and live on honey. Third statement, birds that do not live on honey are dull in color. So now it is not talking about for some bird which is not living, it is talking about birds that do not, means for all. So for all x, if x doesn't live on honey, now we are taking all the, we are not talking about hummingbird, now we are talking about the bird domain. So for all x, not rx implies not of sx. Why? Because sx we have taken as rich in color, and we are saying that do not live on honey are dull in color. So dull in color means negation of rich in color. Rich in color is sx. So what will be dull in color? Not of sx. Hummingbirds are small. Hummingbirds are small. It means we are talking about if it is hummingbird then definitely will be small. So it is for all. For all x, if x is hummingbird then x is small. So for qx, for large bird we have taken qx. So small means negation of large. So it will become not of qx. For all x, if x is hummingbird then x is not large. So is small, not of qx. So this way we have represented our knowledge in predicate logic. Now what is important thing in predicate logic? We can check arguments, the validity of argument. What is an argument? An argument is sequence of statements that end with a conclusion. What is a valid argument? If the conclusion or the final statement of the argument must follow from the truth of the preceding statements or premises. So we are given some premises of the argument, that is an argument is valid if and only if it is impossible for all the premises to be true and the conclusion to be false. What does it mean? If all the premises are true, then conclusion must be true. So if all the premises are true and conclusion is also true, in that case then we say it valid argument. If there is a false value of conclusion when in some conditions all the premises were true, then it is a fallacy. It is not a valid argument. It is a fallacy, or we can call it, it is invalid argument. To deduce new statement from statement, we use from the given statements, we use rule of inference. Rules of inference are templates for constructing the valid argument. So rules of inference are our basic tools for establishing the truth of the statements. So now we'll talk about some rules of inference here. So we are having these standard rules of inference. Now see, if P is true and if P implies Q, if P is true and the implication is true, What does it mean? Means if in if condition, if P then Q is true, it means P is true, and implication is true only when Q is true in case of P true. So directly we can say that Q is true. This is the rule of modus ponens. This is the rule of modus ponens. P and P implies Q. These two are premises, and of these premises implies conclusion will always be a tautology. Second rule of inference is modus tollens. What does modus tollens says? If implication is true, means P implies Q is true, but Q is false, it means P cannot be true. So what modus tollens says? P is false, because if P is true, then Q should be true, but Q is given as false. Q is given as false and implication is given as true, it means P is false. What is law of syllogism or hypothetical syllogism? It says that if P implies Q and Q implies R, then P implies R. This is the law of syllogism. We can use it in our finding of conclusion from the given premises. Okay. Next one is disjunctive syllogism. What disjunctive syllogism says that if disjunction of P or Q is true, it means P or Q, it is true, and P is given as false. So disjunction is true, so disjunction is false if both are false, but we are given one as false and disjunction is given as true, so second cannot be false. So it means Q is true. This is the rule of disjunctive syllogism. Now another rule, addition. What is addition rule? If P is given true, then we can take any ORing. We can take disjunction with any other, that will definitely be true, because P or Q. If we take disjunction with Q, the value is not depending on Q, because P is already true. P is given as true, so definitely their disjunction will be true. Simplification. If P and Q is given true, it means both are true, P as well as Q. So we can take it as true directly, P. That is simplification. Now conjunction. If P is true, Q is true, definitely their conjunction is true. Now a very powerful rule which is called resolution. What is the rule of resolution? Inference, in inference theory, it says that if we are having two statements in clause form. What is clause form? Clause form says that in statement there should be only or and not operator, and implication, double implication, these all are not allowed. What is allowed? Only negation and or. So if we are having P or Q and the other statement is not of P or Q, okay, then it gets, P gets resolved and we will get in answer only other state. In one we are having P, in another we are having not of P. So this will get resolved and we will get other terms in answer. What are other terms? Q and R. Okay, so it will be disjunction of Q or R. This is the law of inference. So we can use these inference rules to find some conclusion, to infer some conclusion from the given premises. So in this video we have talked about predicate logic. For understanding the concept of predicate logic, we talked about propositional logic first, then we talked about premises, we talked about predicates and quantifiers, and then we check the concept of inferences, that is the argument, valid or fallacy, and few rules to find the conclusion. Those are called inference rules. Thank you. Jai Hind.